Hello and welcome to the 19th lecture in this series, and last time I had to stop somewhat abruptly. Let me resume from that precisely that point in the argument. So what we were trying to prove was that, well, that if you have an open set, then the derivative of the inclusion map is an isomorphism. And we are in the process of proving that this map is injective. So I have to prove that the kernel of this linear map is the 0. And I start with the vectors that the DIP V is 0. This by definition means that for all C. So if I take a C infinity function in M, then this V of V composed with I is 0. So as I said earlier, this amounts to saying that the action of this vector, so we want to prove that this vector V is 0, this derivation V is 0. So that would amount to saying that V of any C infinity function on U should be 0. But what we have here is not quite that. We have that V of the restriction of a C infinity function on M to U is 0. So when I start with V in C infinity M and restrict it to U and then act by V, I should get 0. So, but what I want is I should start with an arbitrary C infinity function in U. And I would like to claim that P of C is 0. So to do this, we'll use this small lemma that we have proved earlier. So again, I go back to the previous, in the proof of the lemma, I had this U tilde A and B. I'll use the same notation as in the previous lecture. And then, so we can then what I'll do is I'll just take this C of x, which is defined on all of U, and then I multiply it by this cutoff function f of x, as f of x was as defined earlier. Recall that f of x was a C infinity function on all of M such that f of x was identically, so on this portion f of x is identically 1, and outside that on this green portion outside B, inside A it's 1 and outside B f of x is identically 0. I'll take such a function and multiply it with the function C that I'm starting with here, and I'll call this C1. Well, what is the main property that we want? C1 is C of x if x is in A, because f of x is, as I said here, f of x is 1, and if I'm outside B, then f of x is 0. So therefore the C1 would be 0 as well. And to begin with, since this C was only defined on U, the C1 is also only defined on U. However, it's going to be 0 outside B anyway. So if I extend C1 to all of M by declaring it to be 0 everywhere else as well, then I get a C infinity function on M, and the argument is the same as before. So the C1 is a C infinity function on M, and C1 equal to C on the open set A. How is this C1 going to help us? Well, since C1 and C, these two agree on the open set A, we know that V of C1 equal to V of V of C by that lemma. So this thing here implies this. Also, since C1 is the restriction of a C infinity function on M to U, we have V of C1 is equal to 0 by a hypothesis. That's what we started with. This thing here tells us that the restriction is 0. So C1 is globally defined on all of M, and when we restrict it to, actually maybe to be clear, one should give it a different name. We can extend C1 by 0 to all of M, and let's call the extension as C1, maybe put a tilde. C1 tilde is C1 tilde of X is 0 if X does not belong to U anyway, and inside U it agrees with C1. So C1 tilde belongs to C infinity M, and C1 tilde is identically equal to C on the open set A. These two agree on the open set. Here I don't need a tilde, so it will just. So this extension property is used only in this last step. The fact that when I want to claim that V of C1 tilde is 0. For this part I need this. So right, so then and well, here actually I should use C1 as 0. So just to claim that this C1 equal to that this to get this, I don't really need the extension to all of M. Just on U is good enough. But in the last part, I noticed that C1 is the restriction of a C infinity function. So what I called C1 tilde on M, we have V of C1 is 0. And that's it. So that proves injectivity. Now, as for subjectivity, one would like to say that, so let's start with let W belong to TPM. We want to find V in TPU such that dip of V equal to W. In other words, again, what this really means is that, i.e., if V is in C infinity M, then dip of V acting on phi equal to W of phi. And this we know is the same as V of, as usual. So I just take the phis on M and then phi of I. So, right. So what I want is, so this is the equation which should be satisfied by this vector V that I'm looking for. Well, the natural thing to do is just use W itself, and W is the point is that W acts on C infinity functions on defined on all of M, while a vector V in TPU can act on a different class of functions, those functions which are just defined on U, not necessarily on the all of M. So, but still I can use W to define a V as follows. So we again do the same old trick of this. Let's work with this A, B and this F, this cutoff function F, which is identically 1 in a neighborhood of P and 0 outside this B. So do the same thing. Let U tilde A, B, F be as before. Define V as follows. In fact, this equation that I have here suggests what the definition of V should be. So so the point is V should act on a C infinity function which is just defined on U, not necessarily all of M. So let's start with the C. C belong to C infinity U. And I'm going to use W to define the action of V. Well, as directly I cannot let W act on C because it's defined only on U, not on all of M. However, we know that all that really matters is to see the action of a derivation. We just need to know what it does close to in an open neighborhood of the point, not necessarily in the big open set U. And so what I do is let V of C, I just extend the C to all of, starting with C, I get a function on C infinity function on all of M. I really don't care whether that new function agrees with this old C on U. It's good enough that they agree on this much smaller open set A. Some open set containing P is good enough. So I just define it to be W acting on F composed with F multiplied by C. Note that F composed with C as before, as earlier, gives a C infinity function on M. Again, extension by 0 will give us infinity function. And moreover, inside the open set A, F multiplied by C is equal to C. So, and I define something like this. Let V of C equal to this. Then, of course, I define something, but whether it's I want to check that this equation holds. After all, that's the meaning of I've defined something. So let me check that that equation holds. That equation says that V of also V of, so to check that this equation holds, I have to start with some C infinity function in M. Also, if phi belongs to C infinity M, then this, now that I have a V of, so what I have here is phi composed with I. In other words, the restriction of phi to U. So this according, now I have to use the definition of V. So this is supposed to be W of F multiplied by phi composed with I. That's I'm just going by this here. And well, what are we supposed to check? And this is, yeah, so this is supposed to be, question is this equal to W of phi itself? Oh, well, actually not quite this. So here I should change it a bit. So here I started with C. So here the I does not occur anymore. I mean, there's some slight notational change, because the point is that the C is anyway defined only on the question of putting an I occurs only when you have a globally defined function. So let's leave it like this. Well, so the only question becomes whether W of F multiplied by phi equal to W of phi. And the answer is yes. Again, this equation holds because F multiplied by phi is identically equal to phi on A. Both are C infinity functions on M, and they agree on A. Therefore, the action of W on that is the same, again by that lemma. So this is the equation is satisfied. And one more thing is that, of course, one has to check that this is actually a derivation the way I have defined it, that V of C is let this, so that one has to check that this is indeed a derivation, and that's not difficult to check. So let me quickly do that. One, and V is a derivation. V is a derivation. So what do I have to check? I have to start with V of C1, C2. That's supposed to be equal to W of F C1, C2. So let's check that V is a derivation. By definition, V, so if I start with two C infinity functions, let C1, C2 belong to C infinity U. By definition, I have this. Now, what I notice is that, note that instead of having a single F, suppose I have F squared, F W of F squared C1, C2 is the same as W of C1, C2. Since F equal to F is identically 1 on the open set A. So in other words, these two functions, F squared multiplied by C1 times C2, this is a C infinity function on M, and so is this. On A, both of them agree. Both F and F squared are 1. So these two agree, and therefore W is value of W on acting on that is the same. But writing it in this form makes it easier to check the derivation property. So then I can write it as W times C1 F times W of F times C1 W multiplied by use the other F and use the derivation property of W. So this will give me F at the point P is 1. So C1P W of CF2 plus C2P W of F C1. This is C1P. By definition, this is V of C2 and V of C1. So that completes the proof in all detail. So we have checked that. So along the way, we have also proved various other things. So let's just note them down. So the proof also shows various things. Well, one thing is that this, if f is a smooth function, then I would like to say that the derivative of f as we have defined it in the abstract sense should in some sense coincide with the derivative of f that we started the course with, the classical sense. So, but to make sense of the statement, we have to observe that the classical derivative, so let's say then the classical derivative, I'll put it in quotation marks. So this classical derivative is, let's denote it by df at the point P. This is a map from Rn to Rm again. The classical derivative and the abstract definition derivative. No, abstract derivative is not the right word. Classical derivative and so let's just use the notation df. So classical derivative dfp and this current notion of derivative small dfp are related as follows. So the classical derivative is a map from Rn to Rm. Well, the new derivative is a map from Tp Rn to Tf of P Rm. But we know that there is an isomorphism here, and likewise here. So what the statement one wants to make is that this diagram is commutative. In other words, if I call this isomorphism as phi p and this one as phi f of p, let me stick to phi p, phi f of p. So if I have in this diagram, it's commutative. In other words, df of p, so moreover I need some arrows in specific directions. So this is let's Vp go in this way and V. Right. So then df of p composed with Vp is equal to, well, you do this first. This is just another way of saying that if we identify the tangent space to Rn with Rn itself by this natural isomorphisms that we have, then this the new derivative coincides with the old derivative. For this to, of course, to make sense, it's one need to, it's not enough that TPRN is an n-dimensional vector space. The fact that this derivative and this derivative are the same holds when we use specific isomorphisms from here to here. So this isomorphism, we know what it is. Vp, if I start with an element of Rn, V, that should give me a derivation on Rn, and that derivation is, so it should act on a function, and this is the usual directional derivative. So d by dt of f of p plus tv at t equals 0. This is the, and likewise for this as well. So we know, we have proved that this is an isomorphism, Vp is an isomorphism, likewise Vf of V, and with under these isomorphisms the old derivative and new derivative coincide. And how does the proof show this? Well, it's just a matter of working through the, so for instance here, suppose I want to check this equation, I would start with an element of Rn. So let V belong to Rn. Then I want to check if dp Vp of V, I want to, this is the left hand side of this equation here, and I want to see what it is. Well, the thing is that after all, this final output Vp is going to land here and dfp of that is going to land here. So it's a derivation on C infinity Rn. So I should act it on a function on Rm. So let alpha belong to C infinity Rm. So then it's a matter of plugging in here and checking. So I'll do this next time. Again, I have to stop abruptly in the middle of a proof. So thanks for listening. We'll continue from this point, and then I'll give some more examples of these tangent spaces. Thank you.